Hi folks, so in this video what we're going to do is complete the 2009 Section A questions from the DCG exam, the higher level exam. As always with the DCG paper, there's going to be 4 questions on the Section A, A1, A2, A3 and A4, and on the day of the exam you will have to do 3 questions, but for the purpose of this video, as always, I'm going to do all 4. So starting here with A1, so I'm going to zoom in on that guy there now. So just zoom in on that. And we'll get started. So this question here is based on conics. Just zoom in a little bit more. There we go. This question here is based on the topic of conics. Okay, so this is talking about your ellipses, parabolas and hyperbolas. The question itself says A1, the 3D graphic below shows a beam of light shining across the tabletop and generating a hyperbolic curve. So you can see here a little kind of flashlight projecting light, but where the light is intersecting the table, you can see it's leaving behind what's known as a hyperbolic curve there, and that's probably what we're going to draw. The drawing on the right shows the axis, which is this line here containing the focus, directrix DD1, okay, and focus of such a hyperbola. The eccentricity for the curve is 1.2. Okay, part A, locate the vertex and draw a portion of the curve. So really what we're trying to do is draw the hyperbolic curve here. Now, when we're drawing the hyperbolic curve, it tells us we have to get the vertex, but before we get the vertex, we actually have to put in our line of eccentricity. Now, when we're doing the line of eccentricity, they give you a little measurement here, which is 1.2. Now, if I was to break that over to a fraction, that would be, let's say, 6 over 5. You could say 12 over 10. Usually you kind of break it down, okay? 6 over 5. Now, when I'm putting in the 6 over 5, essentially this is what I do. This is the measurement. I'm going to pop it in there. Excuse me, going up, and then the 1 is going to be the measurement going across. So what that means for my line of eccentricity, where the axis line intersects the directrix line, from that point right there, I'm going to measure across 5 units, and then from that point measure up 6, and that will give me another point on my line of eccentricity. Because technically where the directrix and the axis cross is 1 point on the line of eccentricity, so I need to find another to draw it in. So what I'm going to do is I'm going to measure across 5 units. So from here, I'm going to measure across 5 units. Make sure it's accurate. And I'm going to measure up 6 units. So I'm going in multiples of 10. I'm measuring up 6. There we go. So I went across from here 50 over and up 60 to there. There we go. That there is a point on my line of eccentricity. Okay, now for demonstration purposes, I'll put that in green today. So that there is my line of eccentricity. So I'm just going to write ECC. Okay, now that I've got the line of eccentricity, common rule from the focus, if you project back at an angle of 45 degrees, okay, so 45 degrees to the axis, where it hits the line of eccentricity, drop it down perpendicular to the axis. That there is going to be my vertex, right there. And that is like the top point there. That's my vertex, the top point of the hyperbola. Now that we've got that done, what we're going to do is we're going to draw the method here and complete our hyperbolic curve. So from the focus, what we do is we put in a line here. This line is known as what's known as the latus rectum. I'll pop that in there, going up and down. Probably didn't need to go as high, but I'll pop it in. Okay, and I'm just going to write on that LR. Stands for latus rectum. Okay, funny name. What we're going to do now is we're going to take a series of ordinates. Usually between the vertex and the focus we'll pop in 1, and all I do is I only go up as far as I hit the line of eccentricity. And I go the same height, whatever I do up, I need to do roughly the same down. Now I'm going to do one in between the focus, and I'm going to go out to the end here, and it looks like the space stops out there. So I'm going to go maybe 1 here, go up and down, 1 here, and 1 here. Okay, and I'll pop in 1 more here where the 50 mark is. Okay, so they're known as ordinates. Now what do I do with those ordinates? Well, where each ordinate is, where it hits the line of eccentricity, I'm going to track it across. In this case, I'm going to right over until it hits the latus rectum. There's 1 right here. Then at this point, I'm going to go across to the left. This one, left, left, and left. And there we go. Now, what I do here then is I'm going to take the focus, so I'm going to take my compass and I'm going to position it. I'm going to work off the first ordinate line here. See this little line here where it came up, hit the line of eccentricity and tracked in across. I'm going to take this on my compass, take that distance and mark it going backwards. There we go. I also mark it down here. And now what I've done there is I'm after finding 2 more points on my hyperbolic curve, 1 and 2. Now, there will always be a point where the latus rectum intersects the line of eccentricity. That's always going to be a point right there on the hyperbolic curve, but I need to find it at the opposite side, so I'll take that distance on the compass. I'm going to mark it down the opposite side. Now what I'm going to do is I'm going to track it up using the next ordinate, so from the focus up to here, and rotate in, rotate in, rotate in, and in, and I continue in that sequence. And I always have to find them on both sides in this case. So you can see there, I track it across with the ordinate, that gives me the point, and there we go. And now what I'm going to do is just plot in those points. Now, what do we do then? We have to sketch in our curve, starting at our vertex. Should flow quite smoothly. So we take our time. Excuse me, and we pop that in there. So that there is my hyperbolic curve. Now obviously on the day of the exam, I'll be using a pencil, just for the purpose of the video. Okay, using a little marker. So part A of the question done there. What we did was we had to get our line of eccentricity. So we took the eccentricity, the eccentricity of the curve was 1.2. So broke that down to a fraction at 6/5. And just remember the measurement on top is the measurement up, and the measurement underneath is the measurement in. So from here I went in 5 units, so 5 tens are 50, and then from 50 I went up 60, and that gave me my point on my line of eccentricity. Okay, so the next part of the question here, what we're going to do, it says here, part B, determine the centre of curvature for a point on the curve which is located vertically above the focus. Okay, a little bit tricky here now. This might catch out a few students. Okay, centre of curvature, it doesn't come up too often. But what we're going to do is, it kind of tells us here where it is. Determine the centre of curvature for a point on the curve, okay, which is located vertically above the focus. Okay, so let's locate that point. So we want to find the centre of curvature for a point that is on the curve, okay, and that point is located vertically above the focus. So above the focus, that's our little clue there. So I'm going to draw a line from my focus vertically up, which is actually the latus rectum line. And you can see that little line I'm after putting in there. And where is my point? Well, that's clearly the point right there. And I'm going to call that point P. So what I want to find is the centre of the curvature for point P, essentially. So how do I do that? Well, from P to my focus, I would extend that line down, which is actually already there. So I'm just going to pop that in a little bit heavier now to make it stand out. So you can see that little line there. All I've done is the latus rectum line from P to the focus and extend it on. Now, what I have to do here is I have to go perpendicular to the line of eccentricity. So, T-square out the way here. I'm now going to go perpendicular to the line of eccentricity. So using my set squares. The way I do it is I rotate the 45-degree set square. So I'm just going to set that up. Go perpendicular to the line of eccentricity from point P. Just do a line like that. Now, all I've done so far, I'm going to pop it in yellow at the very end. From P, I located point P because they told me that the point P, the curvature of a point on the curve which is located vertically above the focus. So from the focus I went up vertical to locate my point. Now, the method from there is connect the points through the focus and extend it down. Okay, it doesn't matter if the point was here, I'd follow the same principle. but in this case it just happens to be vertically above it. And then from that point I go perpendicular to the line of eccentricity and I extend it out. Now at that I'm after finding a specific point right here, where that line there goes perpendicular and where it intersects the axis. I now want to go perpendicular excuse me, to that line where it intersects the axis. I want to go perpendicular to that line to intersect this line. So a little bit tricky now. So using this line as my guide, I'm now going to go perpendicular through there. Okay, so I'll pop that in yellow so we can see it now. So now I know how far I have to go down, so we can see it there. So there's that one. Extend this out now in a second, bear with me. I'll pop that in there. And the last step of where that point is, I haven't found it yet. I now need to go perpendicular to this line. Okay? Because that line is vertical, perpendicular in this case is simply a horizontal line. And you'll actually see there, oh nice. There we go. Answer complete. And that is, I suppose, my center point right there for the center of curvature. Okay, so there we have it, guys. Now that is a little bit tricky, okay? Determine the center of curvature for a point, in this case point P, on the curve which is located vertically above the focus. So what we've done is we've found the center of curvature. That's the point that I would use for a point P. And if I was to extend my compass out, well, that's where I would have a tangent line essentially, and it would appear like that. That is my center of curvature. Okay, that goes through point P. So that's the first question done there, guys, which is based on the topic of conics. Now the part B there, not many students might know that. That is quite tricky there, okay? Excuse me. So now what we're going to do is we're going to move down here to A2, which is a question based on the topic of perspective. So pop down here. Okay, I'll just zoom in so we can see it a bit better. Oh, too far, sorry. Okay, A2. The 3D graphic below shows an arrangement of playing blocks. Okay, so you can see we've got this triangular prism on top, we've got a prism underneath it, and another kind of rectangular based prism here. So it's like a triangular prism, a square based prism, and a rectangular based prism. The drawing on the right is a partially completed perspective view of the structure, and you can clearly see they've already put in the yellow block, which is like our cube, let's say. It mightn't be a cube, but it looks like it. Part A, complete the perspective drawing of the base block and of the underside of the triangular top. So they actually ask us to do it here. They're asking us to complete the blue base and the underside of the triangular block. So we can clearly see they've already given us our vanishing points. So it's simply a case of either just extending them out. Now anything that is going in this direction, okay, so parallel with this edge here, this line, let's say in line with my pencil there, everything in line with my pencil, okay, any surface in line there is going in line with this guy, which means it's going to VP1. Any face that is going in this direction is in line with this guy, which means it's going to VP2. Now, that's poorly labelled. Usually we'd label it VP1, VP2. I'll just change that there. Okay, so let's do that. Now, if I look here, the blue block, that's represented by the hidden detail face. Okay, so that means it's going in that direction, which means I have to use VP1. So, from VP1 there, I'm going to go from VP1. They've already actually given us the top edge right there. So all I'm going to do is extend it out to there. Now, how would I find where this point is right here? That's the point I want to find. Okay, so where is that guy? I've actually already got this line. That's the line that I've just extended. But I need to find exactly where this point is. Well, that point is actually right here and it's touching the picture plane. So you can clearly see it's already been brought down for us. So that has to be the point right there. Okay. So now that I've got that point, I can heavy that in, and I'm going to heavy in the edge running down here, which will go all the way down to the ground line, which is this line right here. That's my ground line. Now I've got that, I want to complete the side face here. So from this point here, that's the face running in that direction, which means I'm using VP1. So that goes over to VP1. And how do I complete the back edge? Bring that guy down, And simply a case then of heavying in that surface. Okay, I've got the side of the block. Now I need to get the front of the block. So the front of the block, the face, that face there, is going in this direction, parallel with this guy, which means I'm going over to VP2. So from here, VP2, extend it over, and extend it over. Okay, so that face is going in that direction. Now, how do I actually find the point? Well, there's a couple of ways I can do it. This point right here comes down, because that's the point of where it ends. This point right here is here in the plan view. So where it hits the picture plane, I could drop it down. Or I could actually just extend out from VP1 through here. And that should show me where that edge is right there. Now, we'll prove that, or we'll test that, just to see what my accuracy is like. And see how we doing. Not too bad. A little bit out maybe. And there we go. Okay, so that's not too bad. Right, let's heavy that in. We've done the blue block. Okay, now that I've done the blue block, we'll move up to the underside of the triangular prism on top. So these points right here are the guys I'm basically trying to find, the points on the outside. Where are they? Well, this is the one here, and you've got one over here. So what do? I bring him down to my spectator, which is this guy right here. But what I usually do is I stop him at the picture plane. See how I'm lining it up? I'm just going to stop it at the picture plane. I'm going to do the same with this guy over here. And stop it at the picture plane. Now, what I can clearly see though is that that red face there is in line with the front of the yellow face. So let's look at the direction of the triangular surface. It's going in this direction. That line there is like this, which means it's parallel with that guy, which means I actually have to use VP2 here. So parallel to VP2, or sorry, lined up with VP2 I should say. I'm going to extend that out like that, and somewhere out along that line then is going to be this point here and this point here. So how do I find them? Well, it's where the picture plane, where they intersect and hit the picture plane, the spectator's view. So that's where the spectator would see it when it hits the picture plane. Bring it down. There's that guy. And where's the other one? It's over here. And there we go. So now I found the front edge. It's like I found that guy at the front. So there's that guy. There's that guy. Let's heavy it in. Okay, so I've got that front edge there. Now what I want to do is I want to find the edge running down the back. Now that edge is running in this direction, parallel with this line, which means that it's going to VP1. So from there to VP1, and it'll be the same with this guy. But the thing with that guy is I can't really see it. So I'll just pop it in there. It's kind of hard to see it's going back in that direction. Now, how do I find where this guy ends at the back? I could either bring this guy down where it hits right there, or from VP2, could use this line to go across like that. And in my opinion, it's probably the easiest way to do it. Okay, and there we go. I have now completed the underside of the triangular structure, the triangular top. So part A of the question is done. Part B, determine an auxiliary vanishing point for the 30 degree slope. So they're saying that these sloping surfaces are at 30 degrees. Determine an auxiliary vanishing point for the 30 degree sloping faces of the triangular block and complete the drawing. So let's do that. How do we complete that there? Now what I need to do, and I always do this inside in class, is I look at the surface and I identify the low part and the high part. So if you look at the face, okay, I need to find the direction of the slope. So this is the low part of the roof, this is the high part, this is the low part over here. So if I do that in my sheet, there's low, there's high, there's low. That means the direction of the slope is going up in that, okay, and it's going in that direction. It's not going this way, it's going that way. Okay, it's either going up or going down, whatever way you slope it down, okay, which means that it's going in this direction. That means when I put in my 30 degrees, I have to use this guy to represent that 30 degree inclination for the top surface. So that's the side I use, not this one. So at this point, what I'll actually use here now is a protractor. So with my protractor, I'm going to take the center point of the protractor, and I'm going to use the line, and I'm going to go in this direction. So I'm going to take the center point of the protractor and position it right here on the spectator. Make sure the 0 is sitting out here. Center point of the protractor, okay, and I'm going to measure around to an angle of 30 degrees. So there's my 30 degrees. Now what I'm going to do is, from the spectator, I'm going to extend that line out there. And what I do here now is, I go perpendicular to this line. What I'm trying to recreate here is the pitch of the roof at 30 degrees. I'm going to go perpendicular to that line from where it hits the picture plane. Okay, I'm just going to pop that in yellow there. What I've now got is the height. So that height there, from there to there, that is the height from my auxiliary vanishing point. Okay, so all I've done here is I've recreated the pitch of the roof at 30-degree angle, which we did inside here. That's the 30-degree angle that we did, and I recreated it by creating the little pitch of the roof, a triangle. So what do? I take that height, okay, take that height, and because we did it on this side, I have to do it from VP2. So watch this, above VP2, I take that height and I mark it above VP2, and that then would be known as my AVP, okay, my auxiliary vanishing point. Now I can draw in the roof. So this guy here, to represent the slope, it now goes up to AVP from there. Really simple, okay. What I want to do now, I could get one going down here, but to find the middle of the roof at the top, really simple. There's the pitch of the roof in the middle. Get down there, stop it at the picture plane, then project it down. And there we go. And I connect this guy up to here, and that guy simply connects down to here. And just with my marker now, okay, and there we go. Part B done. So determine auxiliary vanishing point, which we did. We determined that by putting in the 30-degree angle there and taking the height that we got from that and applying it here above our vanishing points to determine our auxiliary vanishing point. Okay, and we had to complete the drawing then, okay, by projecting the right lines. So that's part B of the question done, and part 2 done of the questions. What we're going to move on to now is question number 3. It's top right of the page. So I'm just going to move my sheet there again. Bear with me there. Pop it into the right place. Right, question 3. It says here, a block of cheese standing on a cheese board is shown in the 3D graphic. The cheese has been cut as shown. So you can clearly see there's a little block of cheese sitting on a little board, and it has been cut, a little corner of the cheese taken off. An axonometric view is shown on the right. A plan which has been positioned relative to the axis is also shown. So we've actually got the completed axonometric view here, and we've got the plan view with it. Part A, draw the elevation of the objects in the correct position on the XY plane. So if you look at X and you look at Y here, they're asking us to draw the elevation view. So what do we see if we were looking at it essentially in that direction there? Okay, so I'm clearly going to see the front of the, I suppose, the block here, the cheese block or the board, and then I'm going to see the actual cheese with the cut surface there as well. So I actually have to draw in the elevation view. So how do I do that? Well, all I need to do here is go parallel to the Z-axis from where the axonometric plane is, which is represented by the green triangle, and where it hits the Y-axis, I'm going to go up. So you need a good sharp pencil for this now. And where it hits the X-axis, same thing down here. Okay, and then I'm going to go parallel to the side there, the scaling triangle. I'm going to go out to about here, just so it fits. Okay, now that I've got that guy which is parallel to this line, I need to bisect that and pop in my semicircle. So I'm going to bisect that now, take my time. Okay, So now that I have that bisected, find the middle. So there's my middle, and now I'm going to draw in my semicircle. Take your time. Okay, a little bit of inaccuracy down there, but it's okay. Now, what I do is I extend out the z-axis until it hits the semicircle. Now, when it hits the semicircle, that's going to give me a point that I'm going to create my 90-degree angle with. And there we go. What we've essentially drawn there is the axes for our y. They're in blue here. There's our y-axis. There's our x-axis. And right here we have what's known as a point view of the z-axis. But essentially we have drawn it on the x-y plane. So now we have to draw in the 2D view. I've got the axis where it's going to sit inside there. Now I have to draw the 2D view. So any points on the object, I now need to project them upwards. So everything's going to project parallel to the z-axis. This line here is going to be right on the outside. It goes up as far as there. I'm going to project this guy out. So the baseline, that's on the ground. So it only goes as far as the x-axis there. This is the height. Goes out. I'm going to project this guy up. I'm going to project this point up here. And project up this guy and this guy. I'll get onto the rest in a second. So what we're going to do now is find where these guys are. So these 2 points here, this one and this one, are both on the ground. So if I follow them up, they have to sit on the x line. So it's going to be right there. Follow this one up, right there. These ones have a height, so this guy will go up. That's sitting right on that surface there at the side, the edge view of the YZ plane. So that's going to follow up. It's going to hit right there. So that there is the height of my little block. So how do I put that in? So it's a bit of sliding set squares here, but parallel to the ground, just that line there, and do a bit of sliding set squares. And there we go. I should be able to join this guy like that. And you can see there, we've got that little rectangle here. Now what I want to do is I want to draw in this guy before it's maybe cut. So you can see I've already projected up the line, but how do I find it? Now look, this guy here is sitting on that second surface there. So if I follow it up, it's going to hit right there. So I've got that one. Same with this guy. It's going to go up. It's going to hit right there. So what do I do here now? Parallel to the YZ plane. Sliding set squares. This guy is going to go up. Let's move this over so I can get this done properly. Very little tricky one. Excuse me. So now that I've got that, how do I determine the height of that face here? How do I find this height? So now that I have the line going in its right direction, if you follow this guy out, it's going to hit right there. So once again, that face there, the top surface, is parallel with the, I suppose, the base. So I can use the XZ plane, parallel with that guy. Go across. And there we go. Now let's just heavy in what we can see. So we know what we're doing. Okay, so there is the elevation, not fully done because I still have to put in the cut surface, but how do I find this point? Now that guy is on that top edge and this guy is actually right here on the line, so I actually need to find this guy and this. So it's simply a case of projecting them upwards. It's not right there, it's going to be right in the top. Okay, and there we go. Just pop that in there. At that point, over to that. I join them up. And there's my cut surface. Okay, so part A of the question done. Draw the elevation of the objects in the correct position on the XY plane. So I've done that. That's part A of the question done. Now, part B of the question. It says here, determine the true shape of the triangular cut surface. Okay, there's a couple of ways we could go about this now. I'm going to highlight a couple of little things here. If I want to get the true shape of the cut surface, okay, it's essentially a triangle. What I want to find is, first of all, if I have the length of all the sides, okay, I can just actually draw them down here and draw a triangle like we did in maybe first year graphics. So if we look at that there, have I got the true length of this line here? Let's take, I'm just going to highlight it here. Have I got the true length of that line anywhere? So let's have a little look. In the elevation, I wouldn't have it, because when I'm looking in that direction there, straight at it in the direction, that line is actually slanted away, so it's not a true length there. But what about when I look down on top of it, the object? So when I look down on top of the object, that's there sitting on top, which is that line there. So yes, that line right there is a true length. That's actually a true length. So that's helpful to me. So now that I know that's a true length, that's quite helpful. Okay, so that's the first one. Is there any other true length I can find? Let's have a little look. I want to see, can I find this long one now? So in what view would I see that maybe as a true length? Well, when I look in the face, or in the direction of the face in that direction, well, this would be a true shape. This face here would be a true shape, and because that line is sitting on that face, well then that line has to be a true length. So in what view do I see that? I clearly see it up here. So that's also a true length up there. So I'm going to just write that in. Now the last line is this guy. Now, how would I see that as a true length? Well, that line there is represented by this line in the plan and this line in the elevation. But the problem is, from the elevation, that's a slanted line away from me. In the plan, it's a slanted line going downwards away from me. So neither the elevation or the plan views is that line a true length. So it's not a true length here, and it's not a true length here. We did have the true length of these two, but I don't have the true length of this one. The only way to see the true length of that one would be to take the end elevation or end view. Okay, and that would be taking the view up here, which you can clearly see based on the drawing, they're not kind of letting us do that. So we have to get clever with how we go about this. So what we're going to use is the principle of a rebattement. So we're going to use this line right here. I'll go over now. And that line there is going to be our hinge. And what's going to happen is, if that line acts as our hinge, okay, we've got a point A, let's say, and point B. The only point, if that AB is my hinge, C is going to rotate upwards until it goes flat. And essentially I'm trying to draw in the new true shape. It's like I've taken the triangle and I've rotated it upwards so that I can actually draw it in its actual true shape. And in that case, I'll see the true shape in the plan view because I've rotated that surface upwards. So it's in our plan, we're going to rotate that guy. Now how do I do that? Rotation lines in the plan will appear perpendicular to the hinge. So if we look at the hinge AB, which is this line here in the plan, the point that I'm rotating is this guy. So if I go perpendicular to the true length line from that point, perpendicular, that's like my rotation, okay, and it's really, I've got this true length. Now the question is, do I have the true length of the line AC? Yes, I do. That was this line up here. So if I take that distance there on my compass, and I come down to this point here, and I swing an arc to cut the rotation. Kind of hard to see it there now, but that arc cuts the rotation right about there. It looks like it. Now I can draw in the true shape. So when that, it's like I've taken that triangle and I've hinged it upwards. So just for purposes today, I'll actually pop it in a different colour. I'll go blue. Bear with me. That's tricky now. So that's our true shape right there. Okay, so part B of the question done there, guys. We've got the true shape. Okay, a little bit tricky. I had to identify a couple of true lengths and get clever with how I had to do it with rebatment to do it. So, question 3 done there, guys. Now we're going to move on to A4 at the bottom of the page. So this question here comes from solids in contact, I think. So it says here, the drawing on the right shows the planned elevation of a right cone. That's a cone that just sits on the ground standing upright. A 3D graphic is also given below, and we can see it here. A point P on the curved surface is also shown, so we can see P, okay, in the plan, and that's like P is on the cone, so it's like a point on the outside, out here. Okay. Part A, locate point P in elevation and draw the projections of a sphere which rests on the horizontal plane and which touches the cone at point P. Okay. Step 1. Now it's quite a mouthful. Step 1. All we're going to do is we are going to rotate. Just thinking how I'll go about this. I'm going to locate point P in elevation. I'm going to use it by using what's known as a horizontal cutting plane. So, if I rotate P, this is the apex of the cone now. I'm going to rotate P until it goes to the outside. Now think of this. P is going to be up here somewhere in there. But all I've done is I've taken P, okay, and I've rotated it until it's unknown what is the extreme generator. So if I call this O, that's my apex O. Okay, let's say this was point A, and this is point A. Okay, well look, OA is there, and there's OA in plan. Now, in plan, that line there represents this line in elevation. That line is what's known as the extreme generator. All I've done is I have moved P around until it hits the extreme generator on the line OA. So now that I've found that, what I have to do is I have to find that point. P is in a new position, it's right here. So I need to find it in its new position in elevation. So all I did was I transferred it up. There it is on the line OA. Now that I've found an elevation, I'm going to bring it back, because that arc will appear as a horizontal line in elevation, because it's representing a horizontal cut, and if you cut a cone horizontally across, you'll see a circle. You can see that's the arc of the circle. Now, how do I find P? Project that up, and I found P. So that's P in its correct position. Now, it tells us here though, we've located P. Now we have to draw the projections of a sphere which rests on the horizontal plane and also touches the cone at point P. So I need another, sphere right here. This little red sphere is going to touch or be in contact at point P. Now the problem is, when we do this, we always have to find the size of the sphere when it is touching the extreme generator first. In this case, when point P is on the side. So we rotated P until it was on its position here. I'm going to call it P1, and there's P1. So that's the fake position for P. Okay, that is the fake position, okay, of where we want the sphere to touch. But I have to get it when it's touching the extreme generator first. So how do I do that? Well, the easiest way to do that is you can do a circle of any size. I'm going to extend that line out, or a sphere of any size that touches both the horizontal plane, which is represented by the XY line in the elevation, and the extreme generator, if we bisect the extreme generator and the XY line. So, using A as my compass point, I'm going to put my compass there. I'm going to swing an arc to cut that line. Swing an arc to cut this line. Pop my compass inside here. Swing an arc into the space. Swing an arc into the space. Okay, now where the two arcs intersect, that is the bisector of the angle between the extreme generator and the horizontal plane. Now, anywhere along that bisector, technically, anywhere along that bisector, I can draw a circle that will touch both the XY line and the extreme generator. But I want to find the size of a sphere that will touch the XY line and exactly at point P1, which is not the correct position, but it's the position when it's at the side. Okay, so how do I do that? I have to go perpendicular to my extreme generator. So if I go perpendicular to the extreme generator through P1, at that point right there, that is the center height for a sphere that will touch the XY line and the cone. So now I put it in as what's known as a ghost sphere first. I'm just going to draw in a little vertical line here. So there's my little vertical line. Now what I'm going to do is I'm going to take my compass. This isn't the correct position, but I'll pop it in for the moment. I'm going to set my radius to P1. Check it there now. Yeah. I'm going to draw in what's known as my ghost sphere. Okay, that is my ghost sphere. That is the size of the sphere when it's in the incorrect position, because I need to rotate it around. But now that I've got the center point, okay, of the ghost sphere when it's at the side, I can now draw that when it's at the side in the plan. So the center would come down, and the center would always be in line with the center of the cone. So you can see here I've extended that out. And once again, I'll actually just draw it in, just for demonstration purposes. This is what's known as the ghost sphere. So I'm not heaving it in. You can see it's in very lightly there. Okay, and now what I have to do is I have to rotate it around until it's in its correct position. And its correct position will be on the line connecting from the center of the cone through the point of contact, in this case P. So the center has to be along that line. Like it was along this line going through the fake point of contact, that's where the center was. It now has to be rotated around. So it's like I take a ball and rotate it around the cone. And it's going to rotate about the apex O. So taking the apex, and adjust my compass until it gets out to there, and rotate the center until it gets in the correct position. And now I've found the correct position in plan. Now that I've drawn it, or I've found it, I can actually draw it in finally. Taking my time here now. This is the one now that I would heavy in a little bit more detail. I'll pop that in there. So that is the correct position. That is the correct position of the sphere. Now, I have the correct position of the sphere in the plan. Now I need to find the correct position in elevation. So I have to bring the center point up. Okay, center point is going to be up there somewhere. But what height is that center point at? It has to remain at the same height as it was here. Bring that across. So that's where my center is. Now I have to draw in the correct position of the sphere. We'll heavy it in. Now, if this was drawn fully on paper, because the sphere slightly sits in front of the cone, that should be a hidden detail line, and there should be a little hidden detail edge here because the sphere overlaps the cone in the plan. Okay, so there we have it. That there is the first part of the question. We've completed the sphere and we found it in the correct position in the same point of contact, okay, or in line with the point of contact P. So part B then, determine the traces of a plane which is tangential to the cone and the sphere as shown in the 3D graphic. So what they're asking us to find here is essentially the vertical and horizontal traces of this plane here that is touching both the cone and the sphere. Now, if it's touching both the cone, we're essentially trying to find this line right here. It's touching the edge of the cone, it's tangential to it. Now, how do I find that? The only way I can actually find that is it's going to have the same slope as the cone, okay? But the thing is, I need to essentially imagine I take a cone that has the same angle of the original cone and put it over the top of the sphere, okay? And that's the only way I can draw in that tangential trace, the horizontal trace. So, to do that, what I do in elevation is I need to represent the slope of the cone, okay? So I represent the slope of the cone. No need to draw a full cone. It's going to take the slope of the cone, the extreme generator, and I'm going to go parallel or tangential with this guy. So all I've done, this guy here is parallel with that guy. Okay, I've taken the same slope of the original cone, and it's like I've taken another cone that has the same angle as the original cone and popped it over the top of this little sphere there. Now, all I really need to do that though is because it's like we're putting in a fake cone over the sphere, and where the two cones then, that will obviously give us a plane that would rest against them. Okay, what I need to do with that then is bring that down to the plan. That's going to come out to there. And remember, it's a cone sitting over the sphere, so if I use the center point of the sphere, that will be the radius for that cone then. So now I'm going to draw in a little arch. You don't need to do it fully. I'm going to draw in a little arc. You could draw it in completely if you want it nice and light. That would be the size of my cone in the plan, if I was to draw it in. That would be a cone that sits over the top of the sphere. But more importantly now, I can draw in a tangent between the two of those. Like that. Okay, actually heavy it in. And what I found is that line there, known as the HT, the horizontal trace. But now I also need to find what's known as the vertical trace. But once you have the the horizontal trace, really easy to find the vertical trace. All we do is we can go parallel to HT. I'm going to use the apex of the original cone, 0 or 0.0. I'm going to go parallel to HT. Where it hits the XY line, I'm going to project up vertically, because that's technically representing the wall. And then from O, project across horizontally. And that has to then be a point on what's known as my vertical trace. And voila, we have found our oblique plane VTH. That line there, VTH, VTH. That's the projections of them in the orthographic views. So there's part B of the question done as well, guys. So there you have it, folks. I'm just going to zoom out there, go back out to the original. Okay, so there you have it, guys. That there was the 2009 questions from the Leaving Cert DCG paper, section A. Actually a little bit tricky, okay. There was quite a bit of work in them in comparison to some of the other years, but that was the first year of the new Leaving Cert in 2009 DCG syllabus. So a couple of little tricky ones, especially the part B of this one. The part B in all of them actually was quite tricky, okay. The part A was doable in most of them, but depends on the topics that you obviously learnt inside in class, okay. That was very tricky. Part B of that one was tricky, and even that one as well. Okay, so there you go, folks. That's the questions done. I hope you found those helpful.